Yes, so let me introduce today's speaker in the next seminar in this series, who is Samuel Giuliani. We are very happy that Samuel has agreed to give this seminar to us. And since he's not a local person from the University of Barcelona, I will introduce him a little bit. Um, Samuel started his career in his master's at the Universidad Autónoma de Madrid, working with Luis Robledo on fission. And from there, he moved to the Technical University of Darmstadt for his PhD with Gabriel Martinez Pinedo, where he was extending these fission studies to the R process, so to understand the nucleosynthesis of heavy elements. And after his thesis in Darmstadt, he moved to Michigan State University, where he has been for 3 years, I guess, working in the group of Vitek Nazarevich. And there, Samuel, I think you have expanded these works you have done before to more general energy density functionals, and also you have become expert in Bayesian methods and machine learning applications. And now he's back to Europe, and he will be starting very soon another postdoc in ECT Star in Trento. So Samuel is gonna tell us today about the R process, so nucleosynthesis of heavy elements. We are very much looking forward to your talk. So please.
Thank you, Javier, for the kind introduction. So welcome everybody. I'm very happy to give this seminar and present you a little bit the work that I was doing these last years at MSU, that were mostly focused in the calculation of properties of air process nuclei, and then studying the impact of these calculations for their process nucleosynthesis. So I would like to start this talk with actually a picture that probably is...
I'm sorry, Samuel. I don't think you are presentation mode.
Oh, I'm not?
It looks like I am.
Okay, just let me, okay, because here I put it in a presentation mode. Maybe I can, okay, let me just go out and try it again.
For a second, it was like that.
Okay, yeah. I can just try again. Oh yeah, now I know what was happening, I think. Let me try in this way. And how is it now?
Yeah, perfect.
Okay, great. So let me start with this graphic that probably is familiar to many of you, which is showing the cosmic origin of the elements that nowadays we can observe in the solar system. So what this picture is telling us is that besides the lighter elements, let's say from hydrogen to boron, which are created either during the Big Bang nucleosynthesis or through the destruction of heavier elements heated by galactic cosmic rays, all the rest of the elements that we can see in the periodic table are created during the evolution and possible explosions of different astrophysical objects. Probably the most familiar of these processes is the nuclear fusion occurring in stellar interiors, where actually lighter nuclei are fused together to create heavier ones up to what we call the iron peak. And that actually this is the exothermic process that sustains the stars against the gravitational collapse. So my talk of today, actually, it will be focused on the heaviest part of this periodic table, which actually comprehends what we call the air process nuclei. And a disclaimer that I would like to make at this point of the talk is that despite what this very nice graphic may suggest, whether neutron star mergers are the main astrophysical site responsible for the production of air process elements is still an open question in the community. Actually, even though I'm not going to address this point in my talk, because it's a very interdisciplinary problem, which requires galactic chemical evolution studies, astronomical observations, and so on and so forth, it's important to keep this point in mind, because actually most of the work that we are doing is trying to address this question. So let's start now and look a little bit at the nuclear physics that is behind their process. So this nucleosynthesis process is driven by the competition of two main nuclear reactions that are the neutron capture, which actually produces a nucleus with one more neutron, and the beta decay, where a heavier element is produced by converting neutrons inside the nucleus into a proton. So their process nucleosynthesis occurs in astrophysical sites where the timescales for the neutron capture are much shorter than the timescales for the beta decay. This actually allows the seed nuclei that are present in the environment to capture several neutrons before beta decay, bringing the overall material far from stability and closer to the neutron-rich side of the nuclear chart. So an important characteristic of the R process occurs in the presence of neutron shell closures or neutron magic numbers. This is because the extra stability of these nuclei makes for them very difficult to capture an additional neutron. And this allows the material to suffer multiple beta decays before proceeding further. These beta decays actually bring the overall material closer to stability, where lifetimes are longer, and therefore produce an accumulation of material during the R process. And this accumulation of material actually becomes visible when we look at the solar abundance distribution as is plotted in this inset here, where they are plotted as a function of the mass number. And actually we can see the presence of what we call the second and the third peak that are related with the existence of neutron shell closures at 82 and 126. So now one question that we could ask ourselves is how far can their process proceed in terms of mass number, which is actually given by the number of free neutrons that seed nuclei can capture. So in the case of dynamical ejecta that we can find in neutron star mergers and in other astrophysical sites where neutron to seed ratio are of the order of several hundreds or even thousands, each seed nucleus can capture several hundreds of neutrons and therefore eventually suffer multiple beta decays and cross the whole nuclear chart until reaching the region where fission dominates and nuclei are split in lighter fragment, terminating therefore their process path. So one thing that we can see actually already from this very schematic view of the nuclear chart is that the air process path proceeds very close to what we call the neutron drip line, which marks the line of stability of the nuclear chart on the neutron-rich side, and where experimental data is very scarce or eventually even non-existent, which actually means that the modeling of their process must rely on theoretical calculation of the nuclear properties of several thousands of nuclei. And therefore, there is a huge field of research where we are trying to understand what is the impact of the uncertainties related to the calculation of these nuclear properties and in their process nucleosynthesis. So if we ask ourselves which possible astrophysical sites could host their process nucleosynthesis, we have to understand that actually these conditions where the neutron capture timescales are much shorter than the beta decay timescales can only occur in the presence of high neutron fluxes, which actually is already suggesting that the astrophysical site hosting their process must be a transient object. And this transient object, of course, should have a huge reservoir of neutrons. And actually, a very good candidate for with such characteristic are the so-called neutron star mergers, which are nothing else than the collision of two neutron stars. So as this video is actually showing, two neutron stars orbiting each other can get closer and closer by spiraling in by actually losing energy through the emission of gravitational wave until they eventually merge and produce a short gamma ray burst and other electromagnetic counterparts. Actually, modeling these kind of events is a huge research field right now, where there are many open questions, like, for instance, what is the role of neutrinos and how could they change the neutron richness of the environment? However, something that seems to be quite clear from simulations is that neutron star mergers can produce a large amount of dynamical ejecta, usually between 1,000 and 100 of solar masses, and that this material is extremely neutron rich, which actually seems to provide the perfect conditions for producing what we call a stronger process nucleosynthesis. And actually, what I would like to show you now is a simulation of nuclear network calculation simulating their process nucleosynthesis occurring in neutron star mergers. So what the plot are showing here is the lower panel are the logarithmic abundances as a function of the neutron and the proton number, while the upper panel is showing the same abundances, but as a function of the mass number. Also, what you can see here, these black dots are the observed solar process abundances, which are plotted in the nuclear chart as these white squares, which represent the value of stability. The right panels show the temporal evolution of different quantities, namely the temperature, the density, the neutron to seed ratio, and the average mass number of the material that is produced during their process. You can read the fine numbers here on the upper part of the plots, where you can also see the time describing the evolution, and actually the ratio between the average beta decays to the average neutron capture rates. Just as an indicator, the smaller this number is, the more dominant are the neutron capture over the beta decays. So in this simulation, we start with a bunch of material that is in nuclear statistical equilibrium and that is placed, let's say, around iron. So now, as we let the system evolve and therefore the material expand, drawing the density and the temperature, this nuclear statistical equilibrium is broken, and what we have is that the material starts to capture neutrons and beta decay, forming the so-called air process path. Now, at this point, the material has reached the heaviest region of the nuclear chart. And what you will see now is that fission will start to dominate, and therefore the region around the second peak will start to be populated. Now, the fission fragments produced by these events will actually will populate and shape this lower part of the nuclear chart, but they will also start to capture neutrons, therefore becoming seed nuclei again and giving rise to restarting their process, which actually give rise to what we call the fission cycling. Then what one can see is that after a few seconds from the point when the material became unbound, the neutron to seed ratio is dropped to 0, and what we have is that the beta decay rates start to dominate. This actually brings the overall material to beta decay towards the valley of stability, and eventually shaping their process abundances on a distribution which resembles the one that nowadays we observe in the solar system. The last nuclei to decay are actually the heaviest transactinides. We start to alpha decay and then form the so-called lead peak.
Samuel, just one question.
Yes, sure.
These qualitative features that you have just explained,
are
they model independent on the nuclear theory input that this emulation needs? Are they robust?
Okay. Yeah. Let me say in this way, it depends on Okay, in general, yes, they are quite robust. So mostly, actually, most of any nuclear model, which of course have some information about neutron shell closure, produces this picture. And the point is that, of course, the final outcome depends not only on the nuclear physics that we're putting inside, but also on the thermodynamic conditions, which are given by the trajectory. So what I mean with this is that here we are starting with a particular conditions where there is a very strong, very large neutron to seed ratio, which means that fission will occur, which means that you need your model to know something about fission. And also the temperature are quite high, which means that you are in gamma n and gamma equilibrium. So what I mean with this is that, yes, as long as your model knows something about shell closures and fission, which is something that all global nuclear models know, then yes, you will have a very, very robust description.
I see, thank you. And there's another question by Benjamin.
Yeah.
Yes, so it's related to what you just said. So how do you decide like your starting point? Because we see like you start at N80,
Okay.
N40.
Yeah. So yeah, what is happening here, this is given by nuclear statistical equilibrium. What I mean with this is that temperatures are so high that actually the reactions produced by electromagnetic and strong interactions, they are in equilibrium. Therefore, this actually is, let's say, automatically set by energetic balance. So this actually is quite extremely robust. It's just given by whatever was let's say, the initial neutron richness, and actually what were very few reactions occurring at previous stages, let's say, compared to their process.
But is it like given by some astrophysical? I mean, because is it like something you expect by
you
neutron star merger?
Scenario. Yeah, correct. Actually, let me say in this way: once you know the density and the temperature, okay, actually you can easily set by thermodynamic conditions. You can easily set what is your starting point.
Okay.
So let's say it's more robust compared to regarding the nuclear input. Was there anything else or any other?
I think you can go ahead.
Okay, so yeah, if there is nothing else, then okay, something that actually is important to see here is that this kind of air process nucleosynthesis produces a large amount of radioactive nuclei, which eventually can emit a lot of energy. This, of course, can trigger an electromagnetic counterpart related to this air process nucleosynthesis. Actually, what some studies from, let's say, around 10 years ago show is that the luminosity of this electromagnetic counterpart could be of the order of thousands of novae, and therefore they call it kilonova, which should last around the order, that should peak around the time scales of days. Actually, this is shown here in this plot by Brian Metzger and collaborators, where the luminosity of this so-called kilonova is plotted as a function of time, and one can see actually a typical, one can see the typical decay given by a polynomial law, which is related with the radioactive energy emitted by the air process nuclei. So the important message, or what is important from this kilonova, is that both the shape and the magnitude of the light curve strongly depends in the property of the nuclei that are present in the ejecta. This is because not only these nuclei determine the amount of energy that is released, but they also determine the opacities and the thermalization of the emitted energy, which actually, in other words, is telling us that the kilonova light curve contains direct information about the ejecta compositions that we see that is produced in neutron star mergers. Therefore, the only thing that we needed at this point in order to actually understand whether neutron star mergers and astrophysical side hosting hosting their processes is to observe such kilonova and then compare it with our theoretical prediction. And this actually is indeed what happened in 2017, when firstly the gravitational wave signal from two neutron star mergers was measured by the LIGO Virgo collaboration. And around 11 hours after this event, an electromagnetic counterpart was observed in a galaxy hosted around the Hydra constellation. So what this inset actually showing here is a picture of the same spatial localization 20 days before the merger event, where nothing is visible, and 11 hours after this signal was detected, where we can clearly see the presence of an electromagnetic transient. So when people compare the observed light curve with the kilonova predictions, which is actually shown here in this plot on the left, they found a very good agreement between theoretical calculations and the astronomical observation, which indeed confirm the fact that neutron star merger can host their process nucleosynthesis. Also, what was and what is very interesting is that several models predicted that at late times, the heating rate can be dominated by the presence of very few nuclei. And therefore, the next step was to perform calculations which try to understand which nuclei could eventually leave some detectable fingerprints in the light curve. This actually is a very important question, because if we want to understand whether neutron star mergers are the only or the main astrophysical sites producing air process elements, or whether there must be other objects producing them, is going to be determined by the nuclei that are produced during neutron star merger, and also the relative ratio. And therefore, we have to understand this information that is obtained from astronomical observation as much as possible. Actually, there have been a quite recent study where they found the presence of strontium in the spectra of the kilonova light curve. However, strontium is, let's say, is a relatively light element, and actually we would like to know whether more heavier nuclei are produced, like for instance, Actinides 1. So what several models are found is that the kilonova light curve seems to be extremely sensitive to the presence of fissioning nuclei and translead after emitters at the time scales of several weeks. This is actually showing this plot on the right from Mengru and collaborators, where the luminosity and the effective heating rate are predicted as a function of time. So what we see here as symbols are is the astronomical observations, while the lines are the theoretical predictions. So this red dashed line represents simulations where no fissioning nuclei are present at late times, while this thick green line are the results obtained where even just a relatively small amount of 254 californium is present in the environment. Actually, what we can see here is that the spontaneous fission of these elements produce a bump in the heating rate at time days around, let's say, a time scale, sorry, of around 100 days, which clearly produce a difference in the pattern. Now, the problem is that the astronomical observation of the kilonova were not accurate enough in order to distinguish between these two scenarios, because the open points here only represents the lower limits. However, people are quite confident, or let's say we hope that future observation may eventually have the precision to allow us to distinguish between these two different conditions. Therefore, it actually turned out quite clearly that fission seems to have a relevant, play an important role also for the astronomical observation and the kilonova light curve. And therefore the project that, we started at TU Darmstadt and that I continue at Michigan State University was to employ microscopic calculation of fission and try to understand what was its impact for their process nucleosynthesis. And actually, the fact that fission plays a crucial role during their process nucleosynthesis is something that has been studied already since several years. The most well-known example is coming from probably this paper from Marius Eichler and collaborator, where the abundances are plotted as a function of the mass number. And what you can see here, the dots represent the solar process abundances, and the lines here are the calculations that are obtained with two different fission fragment distributions, where actually we can see the strong impact that these variations produce above the second peak. Now, the problem of studying the impact of fission during their process is that very few theoretical data sets are nowadays available, and most of them are extremely phenomenological or even just simple parametrization, and therefore understanding their validity far from stability is or let's say it's difficult and eventually a little bit questionable. So the long-term goal for us is to try to compute a consistent set of reaction rates and fission properties using the energy density functional formalism. So let me show you.
Sorry, so these phenomenological models for fission, can you say a bit more? What are they based on? Or
okay, so there are so for instance, for the parametrization, okay, there are different cases. For instance, a lot of work has been done assuming, for instance, a 50-50 split. So actually, what you assume is just that all the nuclei splits onto symmetric fragments. The more phenomenological, actually, what they do is they fit the available experimental data using, for instance, a particular number of Gaussians. And then from that, they parameterize it in terms of the neutron and proton number, and they extrapolate to the whole nuclear region. That is, for instance, two typical examples of models that were used. Then there are things that, of course, are a little bit more sophisticated. For instance, you can start to go to more what they call Brownian shape models, where you actually use FRDM interaction, and then what you do is you compute the potential energy surface and look at what is the evolution or you mimic the evolution from the top of the fission barrier and just start to look how you populate the different fragments configuration, and then you can construct the fission fragment distribution. But that is already actually a little bit more sophisticated, and only now we start to have more data sets obtained from such kind of models. Sorry, it was a very diversified question. I don't know if I answered.
Yeah, thanks. I think I got an idea.
So yeah, as I said, our goal actually was trying to use HFB and energy density function in order to provide some more fission data sets. And actually, the way how we study the impact of our results for their processes is given by the following scheme. So we start by computing the fission properties and binding energy using different energy density functionals, and then we convert this nuclear input into stellar reaction rates, basically using the Hauser-Feshbach statistical theory, which is giving us just the probability of a particular nuclear reaction to occur. We then plug these reaction rates into network calculations and then study what is the process nucleosynthesis that we obtain. So yeah, as just a nutshell, even though I think that probably most of you are very familiar with the HFB formalism, let me just give you a very, very a brief reminder of it. So in this formula is the many body wave function describing the nucleus is obtained or is described as a quasi-particle vacuum and is obtained by minimizing the total energy. We then have to introduce some constraining operators in order to construct our potential energy surface, which is needed in order to compute the fission properties, and which is done through the introduction of Lagrange multipliers. Now, the last ingredient that is required is a phenomenological ansatz for the effective nuclear-nuclear interaction, which is modeled through an energy density functional. And in this case, or in the next slides, actually, what I'm going to show you are the results which from the so-called Barcelona-Catania-Paris-Madrid energy density functional, which actually was developed by one of the people at UB. But actually in the market, you can find a plethora of functional, including, of course, finite range interactions or relativistic EDF. So the results that I would like to show you now are the calculations that we obtained for the fission barrier height using the BCPM energy density functional, and then the comparison with other two models that have been widely used in air process nucleosynthesis calculations. So just for those of you that are not familiar with the fission barrier height, this is actually just a proxy telling us what is the stability of the nucleus against fission. So of course, the larger is this value, the more stable is the nucleus against the fission process. So what this plot is showing here is the predicted fission barrier height as a function of the neutron and the proton number for these three different models. And actually what you can also see here is this red dash dotted line, which actually represents nuclei with a neutron separation energy of 2 MeVs. Just for those of you that are not familiar, the neutron separation energy is just the energy required to remove a neutron from a particular nucleus. And these nuclei are plotted here because they give a very good proxy of the location of their process path. So when we compare the predictions obtained from different models, what we see is that in general, there are some similarities among them, like for instance, a kind of enhancement produced around this region of 184, or a kind of banana-shaped region of nuclei with very low fission barriers. However, from a quantitative point of view, the results are clearly very different. And we see actually discrepancy that can be as large as 4 MeVs around the region of their process path. So in order to understand what is the impact of these calculations for their process, we just plug into nuclear network calculation. And what this plot here on the right is showing you are their process abundances in logarithmic scale at a particular time step, that is the so-called freeze out. That is the moment where the neutron to seed ratio is equal to 1, and therefore we don't expect their process path to move further than on average than 1 nucleon. So here, once again, the air process abundances are depicted for different models. And actually what we see is that the prediction of the fission barrier creates a large difference in actually the extent of this air process path. So what I mean with this is that in the case of FRDM plus Thomas Fermi, what we see is that the very low fission barriers predicted here terminate the air process path just at the location of the neutron shell closure 184, and also that the accumulation of material here is smaller compared to the other models because, of course, lifetimes are smaller. The other case for HFB14 and BCPM, which predict the larger fission barrier, these models can accumulate a larger amount of material. In the case of HFB14, actually, their barriers are so high that eventually they can even pass through and populate the region of super heavy nuclei. Of course, this has an impact also in the final abundances, which are depicted here as a function of the mass number. And what we can see is that the larger amount of nuclei that are accumulated in the around 184, then fission and enhance the abundances above the second peak, and they also, the free neutrons that are emitted by this fissioning nuclei shift the third peak towards larger mass number, as actually was already seen also in previous calculations like the one from Marius Eichler and collaborators. But one thing that I would like also to point out is how far is this region from what is the stability, which is plotted here as black squares. And this is important because actually what we see when we look at the kilonova light curve, which is plotted here as a function of time, is that actually the difference in such extreme region leave a kind of clear fingerprint in the evolution of the heating rate as a function of time. So actually what we are seeing here is, what I will call the kilonova light curve as a function of time predicted by these three different models. And actually what we can see is that the three models have quite distinct signatures. Like for instance, if we go back to FRDM plus Thomas Fermi, we see that the low fission barriers that were predicted by these models do not allow any accumulation of this 254 californium, which therefore, and therefore this model does not show any bump produced by the spontaneous fission of this nucleus. Conversely, for HFB14, there is a clear bump, which is actually possible thanks to the higher fission barriers, which allow an accumulation of this isotope. While in the case of BCPM, which has a prediction of fission barrier which is close to HFB14, still this nucleus is not produced at late times, because the large amount of fissioning nuclei that we accumulated during the freeze out produce a lot of neutrons, which then destroys the progenitors of this californium-254 through neutron-induced fission. This is a little bit a mechanism which is similar to the one that we found in nuclear reactors, where you have fissioning nuclei that produce fragments which emit neutrons, which themselves actually induce new neutron-induced fission, and therefore destroy all the material there that is related with fissioning nuclei. So besides the details of the final outcome, the message that I would like to bring is that kilonova light curves are extremely sensitive to regions of the nuclear chart, which are placed very far from stability, which probably we won't be able to access in the next future, and that actually could provide us extremely important information to understand what is the nuclear physics there.
Samuel,
yes.
Regarding to this figure, so
yes.
Since there's big differences between the different predictions, doesn't it look like when comparing this to data, so we are assuming there will be some data in the future for the light curve after 3 months, it looks like there will always be a model that would agree with the data. Is this correct? Or could be that, this is log scale, right? I mean, what we see here, and there's really differences by 2 orders of magnitude. So is it not that whatever the data will be, there's gonna be a model that most likely will be agreeing with that?
Oh, okay. So what you're saying is that the variations are so large that eventually we can always find something that agrees with the prediction. Yes. Is that your question?
That's my impression, but I don't know whether this is correct or not.
Yeah. Actually, I mean, it's yes, indeed. The point is that the impression right now is that variations in the nuclear physics can really produce a large variation on the heating rates or the light curve, which eventually could cover everything. Now, the point is to understand a little bit. So what we are doing here is to look at one particular trajectory. What I mean by one particular trajectory is that we are looking at one particular thermodynamic condition. So let me use other words. Here we see a very strong impact from fission because fission is very strong. But now we have to think that actually these nuclear physics uncertainties should be convoluted with the uncertainty or with different thermodynamic conditions that it would occur in neutron star mergers. So we have different kind of ejecta with different kind of neutron richness. And therefore, it could be that these kind of variations are reduced by the fact that in other ejecta and in other thermodynamic conditions, the impact of fission is not as strong as it is here.
Ah, I see.
So that is one thing. The other one, of course, is that, we need actually to perform more calculation in order to really see what is the kind of variations that we can expect. And also maybe at some point become a little bit more picky about the models that we use. So try to be, because of course you can have any model that could predict whatever. And then at some point we shall probably start to use only models that we know that are physically a little bit more reliable. But yeah, it's a very good point. And more studies are required in order to see when we perform calculations that can directly be compared with observation, because this calculation cannot, since we are just looking at what thermodynamic condition. So we have to see when we perform calculations that can be compared with astronomical observation of light curves, if really the variations are as large as what we're seeing here. My impression is probably they will not, but of course, one has to do that.
Okay, thanks.
Does it answer the question? Okay.
The question.
Okay, so.
May I ask something?
Oh yeah. Sorry. Oh yeah.
Yeah. So I like to know if the rest of the parameters of the nuclear physics input of all these models are the same or are just consistent within the model. I mean, so the beta decay rates and the mass and the masses and so on. So are they the same or for all the models, or they are just their own?
Okay, yeah, so that is a very good point. Actually, so let me say the easy quantities, they are consistent within models. So what I mean by easy quantities is that masses are those obtained from each particular model. So in principle, they are consistent to what are the fission properties. But actually, for the rest, they are not consistent. I mean, I don't know if consistent, if you ask they're all the same between models, yeah, they're all the same. So actually here we are only varying, for instance, okay, let me be more precise. This is, it's a good point. So actually here we were only varying the properties of nuclei above the translead nuclei, because are those where we expect fission to be important. Therefore, what we are doing in our calculation is to use the masses and fission barriers of each individual model consistently. But for nuclei that are below translead nuclei, we are always using the same set of parameters, which is actually given by FRDM plus Thomas Fermi. For the beta decay rates is the same. They are all obtained from one particular model. In principle, what we would like to do is, as you can imagine, is for each model to use beta decay rates, fission properties, masses, obtained all from the same model. But first of all, that is difficult, of course, from a computational point of view. And then there is another question which will be important to know is actually how good is to be consistent in our nuclear input, where the models that we are using are not good in a description of a particular nuclear observable. So what I mean with this is that I will be very happy to actually have my, I don't know, the fission rates, or sorry, the beta decay rates that are consistent with BCPM. But the point is then, if my beta decay rates, is it better to do that? Okay, so to have everything consistent with one particular model, or actually to use the best possible beta decay rates, which can be obtained from another functional. And what I mean by the best is that they better reproduce. We know that they have a better description of, for instance, the experimental beta decay rates, and they better include first forbidden or whatever, even though then they're not consistent with the rest of the nuclear input. Sorry, that was a very long answer. I don't know if I...
No, but it's okay. So it's...
Yeah, so sorry. Yeah, the short answer is no, we are not consistently varying all the nuclear input. what we're doing is just to change masses and fission properties for each particular model.
No, because I was wondering whether the differences between the models are just because of the fission barriers, or is just because something else?
Yeah, right. No, that is a very good question. Yeah, in this case, it's just of the fission barriers, because that is the only thing that we are varying. Fission barriers and nuclear masses, of course.
Mm-hmm. Okay, thank you.
Yeah. Go ahead.
Samuel, you are about 45 minutes now.
Okay. So actually, I'm approaching really the end. Okay, so probably I can just go through the second part of the talk, which is okay. So something that actually it seems to be okay. Yeah, I will just have two more slides, and then probably I will be done. So something that seemed quite clear in this calculation, and that actually it was seen from previous studies, is that an important role is played by fission fragment distributions, and therefore one of the goals that we're pursuing is to obtain a consistent calculation of the fission fragment distribution with the that are consistent. Sorry, a calculation of the fission fragment distribution that is consistent with the fission rates, which is actually is related with the question, of course, that Thomas was doing before. So what I described so far is just related with the probability of a particular nucleus to fission, which is just actually the tunneling produced under the fission barrier, and a way to obtain a consistent description of the fission fragment distribution within DFT is just to model the rest of the space, where actually we are studying the evolution of the nucleus from the outer turning point to the scission point, which is defined as the point where the two fragments are split, is to use the stochastic Langevin calculations. This actually has been used already since 2016 and gave very, very good results. However, there is a problem with this kind of approach, and that is computationally very, very expensive. So just for giving you a more realistic picture, this is the potential energy surface describing the evolution of the nucleus from the ground state, that is this red dot here, to the scission line for, I think, 294 organeson. And the problem is that in order to get this potential energy surface with a decent precision, within around 10,000 points, which most of them are actually has to be used in order to model the evolution from the outer turning line, that is this red line here, to the scission line. And therefore, these are very huge calculations which we can only perform for few selected nuclei, and we cannot apply to the whole chart of fissioning air process system. And therefore, somehow we have to find a simplification of this model that may allow us to perform large-scale calculations. And we did it in a recent paper that was led actually by Gilan Sadukan, where actually what we do is to look at the configuration of the fragment at this outer turning point. We just described the most probable exit configuration of the nucleus when it tunnels under the fission barrier, and we then extract some what we call the prefragments, which actually what we found is that even though we need the modeling of all this space in order to understand what are the most probable final configuration, what we found is that already at the outer turning line, the fragments are very well developed. And therefore, somehow, we could avoid the calculation of all this space here just by identifying what are the most probable fission configuration, just by looking at this outer turning point and using the nucleon localization function. So for those of you that are not familiar, the nucleon localization function, sorry, is just giving you the probability of finding two nucleons with the same spin and isospin on a given localization space. And therefore, the higher is the nucleon localization function, the smaller is this probability, and therefore the more localized are the neutrons, which is given here with this reddish color. So this actually allows us to see the structure, the shell structure present on the nucleus at at this outer point configuration and actually understand what will be the most probable fission configuration. We then actually construct our fission yields by building a microcanonical probability, which is given by the final mass numbers of the fragments and their effective level densities. But mostly they depend on what we call the residual energy, which is just the difference between the ground state energy of the parental nucleus and the fragment binding energy, corrected, of course, by Coulomb.
So there's a question by Benjamin.
Yes, you said you needed like 10,000 points to do this kind of surface?
Yes, this is.
But why? Why do you need that many? And what is sensitive to? Why do you need to be so accurate in this?
Well, this is accurate because actually the point here is that we need not only the potential energy surface, but also the collective inertias. Therefore, because actually the evolution from the outer turning point to the scission line is given by both the evolution, the energetic path, which actually probably is the most important one, but also whatever the inertia is driving you to different configurations. And the point is that in order to be sure that this evolution is smooth and we are not missing some degree of freedom that eventually could drive the nucleus toward more asymmetric or more symmetric configuration, we need kind of accurate results. And the point is that also another thing is that we have to go to very, very large deformation in order to find the scission configuration. So here we are around, 500, 600 barns. And if you think that sometimes we need, this is a two-dimensional space, but sometimes we have to look also at octuple degree of freedom, at pairing degree of freedom or hexadecapole. The more number of dimensions you add, this increases exponentially. And therefore, for that reason, we usually need a very large number of points for constructing this multidimensional space in an accurate way. I don't know if that was.
Oh, yes. Just another question.
Yes.
Because I was, is there a possibility to design an algorithm that is adaptive that adapts the number of points? Because it's something I saw doing in Bruyère-le-Châtel when they do fission, where they build like some, they have a algorithm, I don't remember the name, to adapt the number of points you need to build your energy surface.
Yeah, that actually is, let me say in this way, there is, the way how is done right now, or at least this kind of way, is there is a huge waste of points, because actually a lot of this configuration is not needed. Okay, so for instance, actually it's correct what you're saying, is the number of points is too large, but it's too large because, for instance, all this configuration here is probably useless because the energy are too high, and still we are computing them because we need this configuration at larger deformation points. So yeah, as you said, one could write an algorithm which is way more efficient in the calculation of the points, and just looks, for instance, at what is the relevant path, and just look very, very finely at the points that are just around the relevant regions of fission. But actually the point is that here, if you can do this, everything can be done in independent points, right? So I can send all the configuration without actually too much caring about it. So from my point of view, I think what will be more efficient is to build emulators of this potential energy surface. And what I mean by that is actually it will be way more efficient to have some kind of machine learning algorithm where I plug in just few points that are correctly selected here, or that are properly selected here, and then it reconstructs the surface with a decent accuracy without doing all this calculation. And that is actually what we are working, but I think actually a lot of people are trying right now. Yeah. So just for showing you as a last slide, actually we compute the fission fragment distribution using this method and compare it with experimental results, and which is shown actually here in this plot, where the mass distribution and the charge distributions are depicted for different systems and for different fission modes. And actually what we found is, it's a quite dense plot. So our calculations are given by these blue bands here, while the experimental data is just given by points. And what we see when we compare our calculation with experiment is that we find a quite good agreement in a large variety of systems. Of course, there are some discrepancy, for instance, where the asymmetries are larger, like for this 252 californium here and here, or for some parts of the fermium isotopes. However, I want us to say that the data is not extremely good, and therefore sometimes we found that data sets, experimental data sets, do not agree with each other, and therefore more accurate experimental data will be very valuable for actually understanding better also what is the origin of these discrepancies. We compare our calculation with some global calculations that were performed using scission point model and the Brownian shape model motion. And actually what we found is that the difference between our calculation and these models are quite large. For instance, just as a final remark, for this 252 californium, we see that this very broad distribution that is predicted by manpower of collaborators do not really seem to agree either with our calculation or with experimental data. And actually we see them also in the fermium results here. While, for instance, for the scission point model of Lemaitre and collaborators, we see that actually the nice features that they can reproduce the staggering in charge yields as we do. However, the agreement with fermium seems to quickly deteriorate. So yeah, since I'm actually already over my talk, I will just skip to my conclusions. And yeah, well, I hope I convince you that the observation of the kilonova light curve associated with the gravitational wave 170817 really push their process studies into an exciting here is that actually, in order to better understand the informations that we are getting from this observation, we need better nuclear properties that actually may allow us to understand what is the impact of our uncertainties in the kilonova modeling. And also, I hope I convince you that the density functions can be extremely valuable tools, since we can combine them with Hauser-Feshbach statistical models to compute stellar reaction rates, or use them with Langevin for fission yields or their approximation. And I didn't have time, but eventually we can combine them with Bayesian analysis and try to get an estimation of the uncertainties related with the calculations. I show you a little bit that actually kilonova light curve seems to be very sensitive to the nuclear physics, that it's present in extremely regions of the nuclear chart, like the neutron shell closure 184. But of course, more and better calculations are required in order to really study what is the impact on the kilonova light curves. And yeah, as a future work, we hope soon to extend our calculation of the fission fragments to the whole nuclear chart, and then use them for air process nucleosynthesis studies, and as well as to extend our calculation to other energy density functions in order to capture more what are the systematic variations in our calculations, and eventually try to use quantified nuclear input to perform sensitivity studies of the air process abundances. And just with the last slides, I would just like to thank all the collaborators that participated in this work, and of course all of you for attending this talk. Thank you so much.
Thank you very much, Samuel. It was really a wonderful talk. And we already had discussions, but probably there will be some more questions. Yeah, Benjamin.
Yes, I have a question about at the beginning of your fission part, you described like the 3 steps of your calculations.
Yes, around.
Yeah.
Yes.
Yeah. So if I understand, like the bottleneck in terms of CPU time is the first one, right? As the other are.
Okay, that is a good point. Yes and no. So in terms of calculations, in our case it was. In our case it was, and for a simple reason, because actually we only explore a limited set of thermodynamic conditions. So what I mean is that we compute these properties here, okay, and then we just look at very few results for the network calculation. So one particular trajectory. However, if you want to make, as I said, if you want to make some calculations that then you can compare with astronomical observation directly and not just study the impact of varying one fission properties and see what happened, you have to make more. You have to explore a larger amount of trajectory, which actually will make also this part computationally more expensive. And from this point of view, probably converting the input into rates is probably a little bit cheaper, not much cheaper, but yeah, a little bit cheaper.
And same question, but about, let's say, accuracy or sentence, a bit. How, for example, the second point, is it like completely controlled what you do to calculate the stellar reaction rate in the second point?
Yeah. No, I mean you are right. Also from that point of view, there is